Welcome to Microlecture 37. We're going to talk about the mechanism of SN2 reactions. Okay, so some considerations that we want to make when we're thinking about these substitution reactions are that the reactants are going to be an alkyl halide usually and a good nucleophile. And so we're going to talk about examples of alkyl halides and nucleophiles and being able to identify what would make a good set of reactants for a substitution reaction. The leaving group, as the halide part of the alkyl halide leaves the structure. And so we want to talk about the stability of that leaving group as a product ion. And lastly, what we'll consider is the strength of the CX bond, the carbon to halogen bond or carbon to leaving group bond, and think about what kind of bonds are most likely to break. So some examples of substitution reactions that we're going to come across. Here I have an alkyl bromide, and I'm reacting with a nucleophile. This is a good nucleophile. It's stable, and yet it is it wants to attack something partially positive, as we discussed in the previous video. So I've found my nucleophile. Okay, it's this oxygen, and I've found my electrophile. It's the partially positive carbon atom of my alkyl halide. And we can think about the mechanism, and we can predict products. So my nucleophilic oxygen atom would attack right here at the partially positive carbon atom, and the bromide would be kicked out as a leaving group. So what we just saw here was the formation of a sigma bond. That's what that curved arrow represents, from oxygen to carbon. And so my predicted product will have a new sigma bond, okay, right there. And the rest of the structure is all still attached just like it was. The other product, which you'll come to kind of leave off of your answer eventually, is the bromide ion. But for now, while you're getting used to these reactions, it's good to show all the products and keep the equation balanced, so you know where everything, we're accounting for all of the atoms in the chemical reaction. Alright, so that's one example, and why we call it a substitution is because we're substituting this carbon to bromine bond for this new carbon to oxygen bond. So let's do another one. So here I have an alkyl halide structure, and remember, we don't have to have the reactants written, separated by a plus sign and written before the arrow. We can actually have reactants written on the reaction arrow, so I want you to get used to seeing that. And so we might have something like this written out. Wherever you see a K, that's a potassium, or a sodium, put a plus charge. You know that whatever it's attached to must be minus charged then. Okay, so potassium and sodium, those are metal ions, indicating that you have a salt here. So the negatively charged oxygen is going to be nucleophilic here. The next trick is to find the leaving group. All right, so halides is leaving groups. I've got a couple of choices, it looks like. Does the iodine leave or does the chlorine leave? And here's the thing. We can't have a reaction, a substitution reaction, happening on an sp2 hybridized carbon. We'll talk more about the mechanistic details and why that's the case But for now, let's just say never sp2. Okay, so we want to get used to seeing that this halide, the chloride, is going to be our leaving group, and this delta positive carbon atom is our electrophile. So I've got my nucleophile, it's the oxygen atom, and the negative charge on it is the red flag for that. It is wanting to attack a partially positive carbon atom, so there it does that, and the electrons kick out onto the chlorine atom, making it chloride. And so the products that I would expect here, redraw my benzene ring and redraw the iodine. No reaction happened over there. The new bond that formed was from this carbon atom to the oxygen, and then I still have the two carbons that were attached to that oxygen. They're still attached. So this is my product. The other thing that forms, of course, is the chloride anion. So what we learned there is that the leaving group must be on an sp3 hybridized carbon. One more example, we'll squeeze it in down here at the bottom. Let's have an iodine be a leaving group in a reaction with cyanide. C triple bond N, a couple of lone pair electrons there, a couple of lone pair electrons there, but it's carbon that bears the negative charge in cyanide, the formal -1 charge. So it's actually the carbon atom that is the nucleophilic species, and it's going to attack at this carbon atom because that is the partially positive carbon atom, kicking out iodine as an iodide anion. All right, so the organic product that we get can be drawn like this. And so here we see iodine is a leaving group, and we're identifying nucleophiles and electrophiles in substitution reactions. We're able to identify the bond that is broken, and we're able to identify the bond that forms in each case. So the bond to the leaving group breaks, and the bond between the nucleophile and partially positive carbon atom is the one that is newly formed. So the last couple of things to think about is maybe why are the halogens so stable, right? So we're talking about these guys here, the bromide, the chloride, the iodide. There are leaving groups, and so the product anions should be stable. We have to go towards something stable in a chemical reaction. That's what allows it to go thermodynamically. We want to form something lower in energy. So product anions are stable. I want to think about why that is. We could think about what we know about HBr, HCl, and HI. These are strong acids. Okay, and so their conjugate bases will be weak. Okay, and when something is weak, it is stable. We've talked about first point, we've talked about the second point. The third point here is with regard to the strength of the carbon halogen bond that we're breaking in the reactants. And so for that, we just want to remind ourselves the trend goes by the size of the atom. And so iodine is the largest, and so a carbon to iodine bond is going to be the weakest. We'll just rank them in order here. So iodine being the largest, bromine being a little bit smaller, chlorine being a little bit smaller, and fluorine being the smallest. So iodine to carbon bonds are the weakest bonds, and fluorine to carbon bonds are the strongest bonds. And so the strongest bonds are least likely to break. Okay, so let's talk about some more details of this substitution reaction that goes by the name of SN2. First of all, the reason why we call it SN2, S is for substitution, N is for nucleophilic, and the 2 is for bimolecular. And this has to do with experimental evidence that the rate of the reaction depends on both reactants. Okay, so that's why we call it bimolecular. And so if we have our rate expression written out for this reaction, the rate of the SN2 reaction would be the rate constant K times the concentration of the nucleophile times the concentration of the electrophile. All right, so the reaction proceeds with a one-step mechanism, that means. Okay, that is, both species are involved in the rate-limiting step. We're going to call this type of reaction concerted. All right, and so the other consideration here is with regard to stereochemical inversion. And so I'll draw that kind of below here. Let's say that we have a reactant, an alkyl halide, that contains some sort of stereochemistry. In particular, the leaving group is sitting on a chiral carbon. In a reaction like this, and so let's make it actually chiral by having something different on one side of the ring than on the other. In a reaction like this, okay, let's give ourselves a good nucleophile like cyanide. If the reaction occurs at a stereocenter, we're gonna invert the stereochemistry at that stereocenter. So what that's gonna look like, okay, let's draw our mechanism just for practice. Attack at the partially positive carbon, kick out the leaving group halide. What that's going to look like in terms of the stereochemistry is that the incoming nucleophile has approached from the opposite face, and so instead of being on the dash now, this bond is on the wedge. Okay, that is, the cyanide approached from the opposite face of the leaving group chloride. And so this is how I would draw the expected product with what's called inversion of the stereochemistry. Other considerations here for this reaction are going to be sterics of the leaving group. Okay, so these are factors that affect the rate of the reaction. The nucleophilicity, that's a fun word. How nucleophilic is your nucleophile? So cyanide happens to be a really strong, fabulous nucleophile, but we're going to compare and contrast what, the strength of the nucleophiles in these reactions. And then solvent is another factor that can kind of slow down or impede the progress of a SN2 reaction. Going back to the idea that this reaction is concerted, what that looks like on an energy scale, all right, is that we're going to reach some energy high, and then we're going to come back down and form products that are usually more stable. So in other words, the reaction is usually exergonic with a negative delta G. The point I'm trying to make here is that there's only one hump for the SN2 reaction, and that's because both species were involved in the rate limiting step, and everything kind of all happens at once. And that's going to be something that's going to set this class of reactions apart from the unimolecular reactions, which are going to be stepwise. So the opposite of concerted is stepwise, and you're going to have more than one energy maximum or transition state energy. Okay, so some other considerations that we want to take into account when we're thinking about SN2 reactivity would be the sterics of the leaving group. How big and bulky are the groups around the halide that's leaving. We can classify our alkyl halides as being primary or secondary. And we could even have tertiary. All right, and so we want to think about how likely it is for a nucleophile to attack at these different sites. So let's just abbreviate our nucleophile NU. So NU is nucleophile. So how likely is it for the nucleophile to attack at this carbon versus come in for the attack at this secondary carbon on a secondary alkyl halide? Versus how likely is it for it to come and attack at a tertiary site? That one's even hard for me to draw, so I'm just going to immediately cross it out. We don't do SN2 reactions on tertiary sites because they're too sterically crowded, with 3 R groups on the electrophilic carbon. It's just too crowded. All right, and so we're going to see primary and secondary alkyl halides reacting in this reaction, such that primary are going to be faster reactions and secondary would be slower reactions, but they would still occur. We're going to see a similar trend, like if there's nearby branching going on. So maybe the carbon that's being attacked is open. So these are good examples. This reaction would occur faster, okay? That is to say, if I had a nucleophile attack at this position on a primary alkyl halide, it's going to occur faster than if it occurred here. It doesn't look like much different on the carbon atom that it's attacking, but you've got this nearby bulky group, and that's going to slow down the reaction. Okay, so sterics can be a factor that greatly affects the rate of a SN2 reaction. Another consideration is how nucleophilic is the nucleophile. And so let's just become familiar with a whole class of good nucleophiles. And we're not really ranking them here. We're just going to write out what makes a good nucleophile. So we'll say strong nucleophiles include the following. Now we can have negatively charged oxygens act as nucleophiles. We're going to find that these are also going to be really strong bases, but they can be nucleophiles too. So I'm just going to make a side note, also strong bases, meaning they'd like to attack a proton. And then the rest of our examples that we're going to list out here are nucleophiles that would prefer to attack carbon, and they include acetates and cyanides, for a couple that you have already seen in our few examples that we've done. We could have a negatively charged carbon that is an alkyne carbon. So a carbon-carbon triple bond with a negative charge on the terminal or end carbon atom of that carbon-carbon triple bond. And we could have a negative charge on a nitrogen, so an amide, and we could have a negative charge on a sulfur, so sulfide. Another one that you might see from time to time is N3-, which looks like this. N3-, if I'm drawing out the Lewis structure of it, has a lot of charge in it. So there it is, and it's called the azide ion. And so N3- is going to be another really great nucleophile. It likes to attack partially positive carbon atoms. So a lot of options for nucleophiles that you're going to see in all of the drills and practice problems. I'm sure you'll see all of them at least once. And then weak nucleophiles would include a couple of examples like alcohols and water. Alcohols and water are going to be our weaker nucleophiles, and you're going to see that they tend to not do bimolecular reactions. These nucleophiles tend to do unimolecular, which we haven't talked about yet. For solvents, we want to stick with polar aprotic for SN2. Okay, so these are polar solvents that do not have a proton available to them. So acetone, its structure is this. Just for example, there's no proton, right? When we think of other polar solvents like methanol or ethanol, well, they're polar because they have OH as part of their structure. And this class of reactions proceeds best if the medium is aprotic, so there's no protons around that will get in the way of the reaction, as we'll see later. So solvents can destabilize the nucleophiles and lower the activation energy, and that's why we don't want protons around. Okay, so CH3OH, for example, CH3CH2OH, these are protic polar, and they would not be good for an SN2 type of reaction. They would kind of crowd around the nucleophile and sort of encapsulate it and render it unable to go ahead and attack an electrophile. That would hinder the reaction dramatically.